Last class we talked about orbital velocity and the escape velocity for particular heavenly body. The orbital velocity is the velocity is the minimum velocity required to have any kind of orbital velocity, and the orbital motion. And the escape velocity is the minimum velocity required for example, the satellite to escape from the Earth's gravitational field. So here, one of the interesting questions is that if you have some star, okay, some heavenly body star, so here we know that we calculated the escape velocity. So the escape velocity depends on the mass and the size of the star. Okay, generally speaking, the larger the size, the larger the escape velocity, or the larger the mass. Okay, larger mass means the larger escape velocity, and small size also means the larger escape velocity. Okay, so that's quite obvious because then that means at the surface if you have larger mass or small radius, so the gravitational force at the surface will be larger, so it will introduce a larger escape velocity. Any object, if its moving velocity is smaller than the escape velocity, that means it will force back, right? Okay, to the ground. Now, the question is that what happens if the escape velocity is larger than the speed of the light? So basically speaking, even the light cannot escape from the gravitational field of the star. Okay, so if you send the light from the star surface, okay, and finally it will go back to the star. So you cannot send any light out of the star. Okay, all the stars will emit light. But if the escape velocity of that star is larger than the speed of the light, so even the speed of the light will go back to the star. So it becomes dark. Okay, you cannot see the light sent from the star. So we call it black hole. Okay, so that's a formation of the black hole. And please note that the speed of the light is the maximum speed in the universe. Okay, nothing can be faster than this light. So that means for the black star, nothing can escape from the black hole. Okay. So so that's quite interesting for the black hole. Not only for that, for any black hole, we have something called the event horizon. So inside of this part, if some object, or some, let's say some spaceship, enters this area, it will never come back. Okay, inside of the area is this is the controlling area of the black hole. Okay, inside of the event horizon, nothing can escape. Okay. So here, the first thing. Okay, the next thing we are going to do is try to calculate if our Earth, okay, can shrink to a black hole, what would its radius be? Okay. So to calculate this, we need to note that the speed of the light, c, is 3 times 10 to the power of 8 meters per second. It's a very large speed. Okay. And if our Earth to be forming a black hole, so that means the escape speed, the escape velocity of the Earth should reach this value. Okay? And that can be made by shrinking the Earth to have a very small radius. So at the Earth's surface, you will have a very large gravitational force. Okay. Do you remember how can we calculate the escape velocity? Okay. When we calculate the second and the third cosmic velocity, we're calculating some kind of escaping velocity. So the basic idea is think about the energy. And the surface of the star, okay, you have some velocity. So you have some energy, kinetic energy K0, and you also have the potential energy U0. And if it can escape from the star, so that means the object can go to the infinity. At the infinity, you have K and U. So to barely escape from the gravitational field of the star, so that means you don't need any extra kinetic energy. Okay. So this can be set as 0. Also, at the infinity, the gravitational potential energy is 0, right? Okay. So from K0 plus U0 equals to K plus U. So this is 0, this is 0. This is 1/2 mv squared. And this is negative m e m g, okay, over r equals to 0. Okay, remember how can we calculate the escape velocity? We set this as the actual radius of the Earth. And then we calculate the escape velocity required at the Earth's surface. Okay, I think it's 11.2 kilometer per second. Okay, if I remember this correctly. But now, what we are going to say is that for even this escape velocity, this velocity, it cannot escape. So that means we want to put v for this number and calculate the corresponding radius. Okay? So we're going to see what's the radius. So first let's cancel the mass m. So you get 1/2 v squared minus g me over r equals to 0. V equals to, we put the speed of the light for the velocity of the, okay, and the surface. Okay, and then you get 1/2 v squared equals to g me over r. So r equals to 2g me over v squared. Okay, and now 2 times g is 6.67 times 10 to the power of negative 11. The mass of the Earth, let's check what is the mass of the Earth. We can use 6 times 10 to the power of 24. And this is 3 times 10 to the power of 8 squared. Okay? Let's estimate the number here, the order of the magnitude. Okay. So this is 2 times 0.67 times 6 divided by 3 squared is 9. And now here you have 10 to the power of negative 11 times 10 to the power of 24. And this is 10 to the power of 16 divided, so that means multiplied by 10 to the power of negative 16. Okay? this part, okay, will give us some number. We can estimate it. Okay, we use like 7 figures. So 2 times 7 times 6, it's about 14 times 6, 84. Okay, divided by 9. So it's about okay, so almost 1. It's less than 1. Okay, so we just want to estimate it. And now this number is what's that? 10 to the power of negative 27 times 10 to the power of 24. So it's 10 to the power of negative 3. So this is almost 1 times less than meter. Okay, what's that? 1 millimeter. Okay, so if you want to form a black hole by using our Earth, you have to shrink it to less than 1 millimeter for the radius. Okay, this tiny. So you can think about how dense the black hole should be. Okay, black hole is a very dense object. All the Earth's mass should be concentrated in this small area, a small volume. Okay. So that's black hole. Because if you want to, the speed is huge. The speed of light is huge, so the corresponding radius should be very small. Question?
Where did you get 1 from?
I estimate this number, it's less than 1, probably 0.8 or point something, okay, 0.9. You can use your calculator to calculate it, should be something close to that.
That would be 0.10 or 6.
Oh, should be
It's going to be greater.
10, okay, should be 10. Should be smaller than 10.
9 times 9 is 81.
Yeah, this is, okay, this is about, not 0.8, it's 80 something. So it's about 9 or 10, something like that. So it's not 1 millimeter, okay, 1 centimeter. About.
That's still really small.
Okay, it's still small for this part. Like a ping pong. Okay, so now you can remember this. If so it should be almost like a ping pong if the Earth to be a black hole. Okay. So and you can also try to calculate for other stars, say sun. Okay. What is the radius if the sun has to be can shrink to a
Black hole.
Black hole. Okay. Then here, what you want to do for the mass, this mass, you are not going to use the mass of the Earth. You're going to use the mass of the sun. So it should be larger than this, but still quite small. The black hole is something people predict or propose purely from the theory. And at that time, we don't know if the black hole can actually exist in the universe. But finally, we verified many black holes in the universe. Now people believe that we do have a black hole in the universe. But the question is, how can we know, how can we observe the black hole? Because it's black, we cannot see the light sent from the black hole. So how can we verify the existence of the black hole? So we have to resort some indirect observation. For example, if you have suspected black hole here, okay, and if you have a very large normal star accompanying it. Okay, in the universe there are many so-called binary star systems. Okay, you have two stars very close to each other. In that case, it's possible if they are very close to each other. Note that the black hole has huge gravitational force around it, so it may attract the gas of the star. So the gas will be attracted to the black hole. Okay, so you can know finally all this star will disappear. It will be eaten by the black hole. Okay, and so these gases will move very fast to the black hole. So during the motion, they will emit X-ray. Okay, so by observe the X-ray and do the calculation, we can try to calculate the density of this object here. So if the density is greater than the density required for the black hole, so we can know this is the actual black hole. Okay, so this is indirect calculation. So if we have some, usually we observe those X-ray source in the universe and do the calculation to see if it's possible candidate. Okay, so there are many of them can be verified this way in the universe. So we're actually observing the ray, the light sent from this moving gas, not the black hole directly. Okay. Another question is, can black hole really be formed from a star? Okay. We say that, for example, the Earth, if we want to make the Earth, from the Earth make the black hole, we have to shrink it. But how can we shrink it? Like you cannot push it by your hand, right? You must need to be have some force to shrink the object. Okay, so there is a force can do that. Note that the gravitational force itself is the attractive force. Okay, so if you have a lot of mass, there is a natural tendency the object will shrink to the center. This is called the gravitational collapse. But we still have a lot of different kind of stable stars, planets. Okay, this is why. Because there must be some kind of force against the gravitational collapse. Okay. And the many other forces can provide this kind of resistance so to end up with all kinds of stable objects. Note that without this internal force, all the masses will shrink to the black hole. Okay, what kind of force can provide this resistance to the gravitational collapse? For example, the electrostatic force. Okay, this resistance between the molecules can do this. But please note that the collapse force, this collapse force, gravitational collapse force, depends on the total mass of the object. The mass of the Earth is really small compared to many other stars. So the normal molecular repulsing force is enough to prevent the gravitational collapse. But if you have a very huge star, like the Sun, okay, or maybe larger than the Sun, then the normal molecular repulsing cannot compete with the gravitational collapse. Then it will further shrink to even denser object. But then there are more forces will be introduced. Okay, if you push the molecules and atoms into very small area of volume, okay, so the molecules and atoms, and even the nucleus will be breached. And so you are going to have all these like protons, okay, neutrons or electrons, okay, they are not going to bond it in the atoms. You will have these, okay, free electrons, neutrons, and protons. So first, okay, if we keep increase the mass of the star, okay, up to some mass, it will break the atom. So you are going to have a lot of free electrons. Then the resistance, we call it the degenerate pressure of the electrons, will be back, okay, can compensate, okay, or compete with the gravitational collapse. So for some mass, when the electron repulsing, okay, can compete with the gravitational collapse, it will form the so-called the white dwarf star. Okay. These are quite this white dwarf star called dwarf white because it's usually the white color dwarf because it's very small, it's very weak. Okay, star. So for the small mass, okay, before that is some normal star. Okay, and then if you have very large normal star, finally it will be shrink further. The electron repulsing cannot compete with that. So then it results to, okay, then it will further, the gravitational collapse will further break the nucleus. So you are going to have the free neutron. Okay, you know in the nucleus you have the neutron and the proton. So if the neutron repulsing can compete with the gravitational collapse, you are going to have the so-called neutron star. Okay, that's much denser and smaller than the white dwarf star. And if you have even larger mass, even the neutron repulsing cannot compete with the gravitational collapse. So what we know is that so far we know that all the masses will be collapsed into one point. Nothing can compete with the gravitational collapse. Then we have the black hole. Okay. So you can see the own mass of the object itself will determine its final fate. Okay, what kind of fate you are going to have is completely determined by its own mass. For example, the Earth, it will not go any of them. Okay, it's quite small. It just will remain its normal form. Okay, in the universe, it will keep that, and until it be destroyed by some other stuff, okay, like the sun explosion. And our sun, the final fate of our sun can only be white dwarf star. Okay, because our sun is quite a small star in the universe, but there are many huge objects. Okay, many huge stars in the universe. They will finally form the neutron star and the black hole. And one thing is known that before these things happen. Okay. Before this is happen, usually there is a stage called supernova. Okay, nova explosion or supernova explosion. Okay, at that time, the normal star will explode. Explode, and so it will be very bright in the universe. So that's called the supernova star during that stage. How bright can it be? In fact, in about I don't remember exact year. Okay, and this year there is a supernova explosion in the I think in the maybe Cancer or which constellation, I don't remember. Okay, but during that year, because of the supernova explosion, for almost 1 month there is no night. Okay, that star makes the night just as daytime. Okay, so the light of the star can be compared with the sun. That's very bright. It's observed at the remnant of the supernova explosion ended up with as Crab Nebula. Okay, Crab Nebula. And inside of the Crab Nebula, there is what's called a neutron star or black hole. Okay.